Hello students, welcome to Educate. Today we are going to start next chapter of NCERT Physics, Systems of Particles and Rotational Motion. So you know different types of motions. So rotational motion means body is rotating. Here, in addition to rotational motion, there will be translational motion also. So we will see such situations. Before that, I would like to define a rigid body. So what is rigid body? A body which does not change its shape on applying force. Although there is no any strictly rigid body, but for particular purpose we can take certain objects. So here we can read it. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. Ideally, a rigid body is a body with a perfectly definite and unchanging shape. The distances between all pairs of particles of such a body do not change. It is evident from this definition of a rigid body that no real body is truly rigid, since real bodies deform under the influence of forces. But in many situations, the deformations are negligible. In a number of situations involving bodies such as wheels, tops, steel beams, molecules, and planets, on the other hand, we can ignore that they twist out of shape, that they warp, bend, or vibrate, and treat them as rigid. So, this is rigid body is an ideal concept, so that practically does not exist, but still for our study purpose with certain assumptions we will consider a rigid body. So here you can see there is one box which is sliding down. So here, if you consider the velocity of particle P1 or velocity of particle P2, so that is uniform. Means there is translational motion and any point like P1, P2 will move with the same velocity. Now consider this situation. Here there is one important point. In pure translational motion, at any instant of time, all particles of the body have the same velocity. Now this is another situation in which body is moving down and there is a rotation. So in that case you will observe that velocities of all 3 points like P1, P2, P3, etc. will not be same. So here in detail it is given a rolling motion of a cylinder. It is not pure translational motion. Points P1, P2, P3 and P4 have different velocities shown by arrows. Its velocity in this direction, it is in this direction. Here it is in contact. So its velocity will be 0. In fact, the velocity of the point of contact P3 is 0 at any instant if the cylinder rolls without slipping. Now, so you can say, so there is translational motion and another type of motion will be rotational motion. So for rotational motion, there must be an axis of rotation about which body rotates. Here phi is shown, so this is axis of rotation about which it rotates. Similarly, here Potter's pot, here he is creating the pot, so it is moving around like this. So there is center, means axis of rotation. So different situations can be visualized in which rotational motion is there about an axis, and that is called axis of rotation. Here This is one body which is rotating about fixed axis. So here there is one particle which is describing this circle. There is another particle which is describing this circle. There is one particle here which is on the axis, so it will remain stationary. So it can. So here this is axis of rotation. If you read it here, a rigid body rotation about the z-axis, each point of the body such as P1, P2 describes a circle with its center C1 or C2. It depends. Suppose axis of rotation becomes this, then body will start moving like this. So different radii will be there. So here every particle of the body moves in a circle which lies in the plane perpendicular to the axis and has its center on the axis. So for this or for any other point. So figure shows the rotational motion of rigid body about a fixed axis, z axis. So such thing is possible. So now if we consider the motion of the top, here top is rotating. So there is no fixed axis. It can't rotate with about a fixed axis. So here it will describe a cone, but at this point will remain fixed. So spinning top, the point of contact of the top with the ground, its tip O is fixed. Here there is axis of rotation from blades. Here fan is rotating. So here again there is oscillatory motion. So an oscillating table fan with rotating blades. The pivot of the fan point O is fixed. The blades of the fan are under rotational motion, whereas the axis of rotation of the fan blades is oscillating. So many such examples you will find if you read it. The point of contact of the top with the ground is fixed, as we have seen here. This now you have to read it. Now we are considering this type of motion. Here object is shown, so its top remains vertical. Yep. So this is translation motion. Motion of a rigid body which is pure translational. But here axis of rotation is also moving here and there. You are seeing that at this time axis of rotation is this, here axis of rotation is like this, here axis of rotation is like this. So in this case you can say there is translation motion as well as there is rotational motion. Now you can read this. The motion of a rigid body which is not pivoted or fixed in some way is either a pure translation or a combination of translational and rotational. The motion of rigid body which is pivoted or fixed in some way is rotation. So the rotation may be about an axis that is fixed, that is ceiling fan which has fixed axis, or moving oscillating table fan. So this type of things are there. Now there is one important concept called center of mass. So center of mass is that point inside or outside a body where it is assumed that entire mass is concentrated. See the situation. Suppose you have a ring. So its center of mass will not lie on the ring, it will lie somewhere here. But suppose you have a sphere. So its center of mass will lie at its center. If you have a rod, so its center of mass, if mass is uniformly distributed, in that case its center of mass will lie at the center. So we have to find out expression for center of mass, and with that knowledge we will see how the object moves, and we will do some calculations, be it translational motion or rotational motion. Here suppose there is a body and mass distribution is given. Suppose here with respect to origin, suppose here there is one mass m1 and its distance is x. There is another mass m2, its distance is y. So suppose we have to find out position of center of mass. So say center of mass lies here at distance z, or we can say axiom, we can write suppose axiom. So what do we do in that case? We will write first mass into its distance, then second mass and its distance, say it is y, so we write here y divided by m1 plus m2. So we are going to write more generalized form of center of mass. Here mass distribution is given. Suppose there is a irregular body, and from center of rotation, this is line of rotation about body rotates. So suppose here m1 distance is x1, then m2 distance is x2. Similarly, say m3 distance is x3, like this. So xcm, if here coordinates are in y terms also, so we can find xcm, ycm both. So xcm when we find, so we take m1 x1 plus m2 x2 plus dot 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 plus mn xn divided by sum of all masses m1 plus m2 plus dot dot plus mn, and this can be this is m, we can write m1 plus m2 etc as m1 plus m2 plus dot 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 plus mn. So this can be written as xcm equal to m1 n1 m1 x1 plus m2 x2 plus mn xn divided by capital M. That can also be done. Here sigma sign can also be used, mixi, so that we will see later on. So in case of two body system, suppose xy coordinates of RCM are to be found. In that case, xcm we can find, ycm we can find. m1 x1 plus m2 x2 divided by m1 plus m2. Similarly, m1 y1 plus m2 y2 divided by m1 plus m2. If it is 3D, in that case ZCM can also be found. If three body system is there, in that case we extend this. So xcm will be m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Similarly, ycm will be m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. Now this can also be written as I told you, in 3D system we can summarize the position of center of mass. So x can be written as sigma mixi divided by sigma m. Sigma m can be written as capital M. Similarly, y will be sigma miyi divided by sigma m, and as I told you, sigma m can be written as capital M. So in denominator you can write capital, and z will be equal to sigma mi zi divided by sigma small m, which will become capital. So this is how we can write the position of center of mass. Now if it is given in vector form, then also it is possible that different masses are given and their position vectors are given. Suppose m1 is 2 kg and its position vector r1 is say 2i cap plus 3j cap plus k cap, and m2 is 4 kg and vector r for this is given as I cap minus j cap plus 2k cap. In this case, x cm, so not x cm because vector r involves all three components, just write r cm in vector form will be equal to m1 vector r1 plus m2 vector r2 divided by m1 plus m2. Now this can be broken into xcm, ycm and zcm, means xcm if you take component, then x components after putting value. Similarly ycm you can find and zcm you can find. I think you have understood how to find after putting the values. I coefficients if you write, then xcm you will get. If you write coefficient of y, sorry, coefficient of j, you will get y, and if you take coefficient of k, in that case you will get zcm. So you have understood basic concept. Here there is one important point. The important point is, note the economy of expressions we achieve by use of vector if the origin of the frame of reference, the coordinate system, is chosen to be the center of mass. Then this thing, sigma mi ri will become 0. So this point you have to keep in mind. Later on we will do some questions based on it. Now here the same thing, if there are a large number of particles, in that case sigma can be replaced by integration symbol. So in that case we can evaluate it as by using integration symbol. So we say RCM can be written as 1 upon m times integration r, and after that we can write dm. So this is vector, this is vector. And again, if we choose the center of mass as the origin, in that case r will be 0, so r dm will be 0. So in that case x dm, y dm and z dm will become 0. So now we are going to see one question here. Question says, find the center of mass of three particles at the vertices of, find the center of mass of three particles at the vertices of an equilateral triangle. Here these are the particles and masses are given as 100 gram, 150 gram, 200 gram respectively. Each side of the equilateral triangle is 0.5 meter long. So here we have to find out the coordinate of center of mass. So for that, let's analyze the situation. So let's draw the triangle here. This is equilateral triangle and we take this as 0, 0. And this is x-axis. Side of the triangle is given as 0.5 meter. So up to here this will be 0.5. And this point will be just half of it, 0.25 in terms of meter. Now one mass is here. Suppose this is 100 grams. Either you write 0.1 kg here. Another mass, say 150 gram or 0.15 kg is kept here, and we have to write the coordinates. This is 0, 0. Here x coordinate is 0.5, y coordinate will be 0 because it lies on x-axis. We are taking coordinate axis. This is y-axis. We have to find out the x and y coordinates of this mass. So here this is at midpoint, so 0.25. Now you have to find out y coordinates. So you can apply Pythagoras theorem. This is 0.5, this is 0.25 up to here. So this h, if you find, then that will be y coordinate. So if you evaluate, that will come out to be 0.25 root 3. So you have got, this is xy, here also xy pair. So if you find xcm, so what will you do? You will take m 0.1 into x coordinate, it is 0. Then you will take this point 0.5 into mass, this is 200 gram, that is 0.2 kg. So 2 plus third mass you are going to take 0.15 into 0.25 divided by sum of three masses. So 0.1 plus 0.15 plus 0.2. You can evaluate it. So you will get xcm. Now we have to find out ycm. So for getting ycm, thing is very simple. Again, you will take y coordinates. First one will become 0. Second one will also become 0 because here, so 0. Only third one will be there. So that will be 0.25 root 3 multiplied by mass is 0.1 and divided, 0.15 divided by total mass 0.1 plus 0.15 plus 0.2. So this is how you will get xcm and ycm, and it will lie inside somewhere here. So that will come out to be 5 by 18 after evaluation, and second one will come out with 3 root 3. So I think you have understood how to evaluate the position of center of mass. Now we are going to see another question. Here question says, find the center of mass of a triangular lamina. So in this case, very simple thing. We find the median, and intersection of the median will be the position of center of mass. If you remember, the point where median intersect, that is called centroid. So our answer will be the center of mass lies at the centroid. Here you don't have to calculation unless the coordinates of the vertices are given. So thing is clear. Now we are going to choose, or we are going to do this question. Question says, find the center of mass of a uniform L-shaped lamina, a thin flat plate with dimensions as shown. The mass of lamina is 3 kg. So here what shall we do? We will try to divide the lamina. This is L-shaped lamina, this is clear. So here it is divided into 3 parts. So mass was 3 kg. So each part will have mass 1 kg, 1 kg, 1 kg. Now another point that is left is to locate the position of these masses. So what is the position of this mass? What is position of this mass? What is position of this mass? That is important point. So up to here, this is 2. Here it will be 1.5. Here it will be 1. Here it will be 0.5. So for this, if you find x coordinate, so it will be 0.5. Y coordinate, here up to here it is 1. It is just midway. So it is 0.5. Correct? And as I told you, mass is 1 kg. So this is coordinate, first coordinate x1, y1, and this is m1. Now consider the situation of this mass. So mass is again 1 kg. What is x coordinate? So here x coordinate, as you observe, 1.5. And what is y coordinate? Again it is halfway, so 0.5. So you have got the y coordinates also. Now consider this. For this, mass is again 1 kg. and x coordinate will be 0.5 and y coordinate will be 1.5. 1.5. Now, if you want to find out xcm, so very simple. If you take this as x1, y1, this as x2, y2, this as x3, y3. So here m1, m1, all here m1 equal to m2 equal to m3 equal to 1 kg given. So it's simple. So I'm not writing them. So this will become x1 plus x2 plus x3 divided by 3. Now write the coordinates of x. Similarly, ycm you can find my1, m is 1, so y1 plus y2 plus y3 divided by mass is 3 kg. You can evaluate. Okay, let's see what is given here. So here same thing is given, m times x1 plus m times m is 1 kg and x1 y1 here, sorry, x1 x2 x3 then 3 kg. So these are, so we have got the coordinate of center of mass as 5 by 6 and 5 by 6. Okay, now motion of center of mass if we consider. So for that, total mass and position of center of mass we write, that is capital M times R, and then we split it for each particle. So we write either sigma MIRI, which is equal to M1 R1 plus M2 R2, and here R1 R2 are the position vectors of those particles. Now we do one thing, we differentiate it with respect to t. So we just write dr upon dt. So here dr1 upon dt plus dr2 upon dt plus dr3 upon dt, that is clear. And you know dr upon dt is velocity. So m times v equal to m1 v1 plus m2 v2 plus m3 v3 plus dot dot mn vn, no doubt. Further, suppose we want to convert it into acceleration, because our purpose is to write the expression for force. So here further we differentiate, we write it m dv upon dt equal to m1 dv1 upon dt plus m2 dv2 upon dt plus dot 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 plus mn dvn upon dt. So dv upon dt is acceleration. So what we get? We reach here, we have got ma equal to m1 a1 plus m2 a2 plus mn an. So this is force, right? So ma equal to, here first force F1 then F2 plus Fn. So we can say from Newton's second law, the force acting on the first particle is given by F1 equal to m1 a1, similarly for this m2 a2 and so on. So we have got final expression that ma equal to F1 plus F2 plus Fn. Up to here I think there is no problem, and if we find the sum of these forces, so they will be equal to external force applied. So we can write ma equal to F external. So here meaning of this expression is given, the center of mass of a system of particles moves as if all the mass of the system was concentrated at the center of mass and all the external forces were applied at that point. So when mass is distributed, in that case we try to find out center of mass so that calculation may become easier. Here some more information is given, let's read it. Notice, to determine the motion of the center of mass, no knowledge of internal forces of the system of particles is required. For this purpose we need to know only the external forces. So to obtain this, we did not need to specify the nature of the system of particles. Here the system may be a collection of particles in which there may be all kinds of internal motions, or it may be a rigid body which has either pure translation motion or a combination of translation and rotational motion. Whatever is the system and the motion of its individual particles, the center of mass moves according to equation that we have derived. This equation ma equal to F external. So Our next point is here. What is happening? Here a cracker is thrown like this. At this point, this is direction of, or this is path of motion of center of mass. Now what happens? At this point there is explosion, means cracker burst. So different fragments will move in different direction. But what will be the path of center of mass? So it will remain same. The same thing is given here. The center of mass of the fragments of the projectile continues along the same parabolic path which it would have followed if there were no explosion. So a projectile, here we can read it. A projectile following the usual parabolic trajectory explodes into fragments midway in air. The forces leading to the explosion are internal forces. If they are internal forces, then direction will remain same, or direction will remain usual. So if there will be external forces, only then the direction will change. They contribute nothing to the motion of the center of mass. The total external force, namely the force of gravity acting on the body, is the same before and after the explosion. The center of mass under the influence of the external force continues, therefore along the same parabolic trajectory as it would have followed if there were no explosion. So this is logic here that you understood. Now another concept is linear momentum of system of particles. So it is again simple. We consider linear momentum of all particles, then we sum up. So we can say total linear momentum is P equal to P1 plus P2 plus Pn, and you know P equal to mv. So m1 v1 plus m2 v2 plus mn vn. So we can say P equal to mv for center of mass. So the total momentum of a system of particle is equal to the product of the total mass of the system and the velocity of its center of mass. The same thing can be written like this. And now suppose we want to convert it into force. If you remember, change in momentum with the time is called force. So here dp upon dt, we find mass is constant, so dv upon dt, and dv upon dt can be written as acceleration. So this is net force, so dp upon dt is external force. So we have got that Newton's second law of motion extended to a system of particles also. If many particles are there, still Newton's second law means F equal to ma. That can be applied. Now see the situation when momentum means linear momentum remains conserved. So it will happen only when external force is 0. So if external force is 0, then dp upon dt will become 0, and if you know that derivative of any constant becomes 0, so that is why p remains constant. The same thing is stated here. When total external force acting on a system of particles is 0, then the total linear momentum of the system is constant. This is the law of conservation of the total linear momentum of a system of particles, because this also means that when the total external force on the system is 0, the velocity of the center of mass remains constant. Of course, if p is constant, so p is a mv, m cannot change, then v equal to constant. Now, here we are considering one radioactive particle. It is moving in this direction, and at this point radioactive disintegration takes place, in which radon and helium atoms are produced. Suppose helium goes in this direction and radon goes in this direction, then what is the direction of center of mass? So it will remain as usual. So center of mass will move like this. Now here if you read what is given, so you will notice that same thing as I told you, a heavy nucleus radium splits into a lighter nucleus radon and an alpha particle nucleus of helium atom. The center of mass of the system is in uniform motion. Second, here what do you observe? Here radon is going in this direction and radium was going in this direction. So again same thing, the same splitting of the heavy nucleus radium with the center of mass at rest. The two products particles fly back to back, so that since center of mass initially was at rest, so it will not move because here there is no external force. So what happens? If you calculate the momentum of this and momentum of this, so they will be equal and opposite, hence they will get cancelled. So rate of change of momentum will remain 0, so it will not change. So I think you have understood that in absence of any external force, the direction of center of mass remains unchanged. Here another observation is shown. Here helical path is shown. So let's read it. What is given? Trajectories of two stars. Here two stars are given. One star is here, one star is there. So here this is trajectory of one star, this is trajectory of another star. So what will be the trajectory of center of mass? So center of mass will move like this. Trajectory of two stars, S1 dotted line as shown, and S2 solid line, forming a binary system. Binary system, you understand? There are two particles. So here direction of center of mass is shown. Similarly, in this case, binary same thing, motion in this direction, motion this. So center of mass will lie over here. The same binary system with the center of mass C at rest, because this is moving in this direction. This is, so they are equal and opposite. So momentum due to this, momentum due to this will cancel out, and hence center of mass will remain at rest. Here both the stars are moving forward. That is why center of mass is also moving in the same direction. Now here, if you wish to read, so little information is given. In astronomy, binary double stars is a common occurrence. If there are no external forces, the center of mass of a double star moves like free particle as shown in the figure. The trajectories of the two stars of equal mass are also shown in the figure. They look complicated. If we go to the center of mass of frame, then we find that the two stars are moving in a circle about the center of mass, which is at rest. So second case, as we have discussed here, this happens. Now we are going to see some other interesting facts, like vector products of two vectors. So we have already studied some basic concepts like dot product, vector A dot vector B, or vector B dot vector A gives AB cos theta, where A is modulus of vector A and B is B equal to modulus of vector B. So this is called dot product. Here we need cross product. Means suppose vector A cross vector B, if we want to find out. So modulus A, that is say A, and modulus B, and then sine theta. And since this is a vector, so there must be a vector. So here we write unit vector that points in perpendicular to these two. What does this mean? If vector A is along x-axis, vector B is along y-axis, then A cross B will be along z-axis. Why? The cross product of two vectors will be third vector, which will be perpendicular to both these vectors, whose product is the resultant. So I think that you have understood. One more concept is there. A cross B, if you change the order, then negative sign will appear, B cross A. Now, the same thing is shown here. A cross B is shown by here rule of right-handed screw for defining the direction of the vector product of two vectors. Rule of, so instead of this very simple rule, you should memorize that you just write in circular order. Suppose you write here I cap, then J cap, then K cap. If you move in the direction of arrow and you take cross product, then third vector will be the result. Like if you write I cross J, you are moving in order, you will get K cap, right? If you take J and K, J cross K, you will get I cap. Similarly, if you take K cap, I cap, you will get J cap. But if you move reverse, means opposite to the arrow, if you take j cross I, in that case you will get negative of third vector minus k cap. So this is how you can easily determine the direction of third vector, but you have to keep in mind that the resultant of cross product of two vectors is always perpendicular to two given vectors. And as far as properties are concerned, so we can find cross product of any two similar vectors or same vectors will be 0. Why? Because see, vector A cross vector A means modulus A times modulus A times sine, and since same vector, one vector is like this, another vector is like this, so theta will be 0 degree. So here sine 0 degree, and 0 degree is going to give 0. So ultimately result will be 0. For example, practically if we suppose we have velocity times momentum and we want to find out what is the result. So in that case, what will you do? Just check. This is velocity and here this is mass into velocity. Now mass is constant, take it outside, then write velocity times velocity. Same situation will be there, same vector. So theta will be 0 degree, thereby your answer will be 0. So such situations you will come across. So we will discuss them. And in case of vectors, distributive property applies. Suppose vector A and inside there is vector B, here vector A cross vector B plus vector C. Suppose you are given. So A cross B plus A cross, you can write. So nothing will happen. Now, same thing is given here, and cross product can also be found. Cross product can also be found by using determinant method. We have already studied about determinant method. Suppose we take simple determinant. So determinant symbol will be like this. Suppose we are taking 2 cross 2 determinant 3. Let's take numerical values, so that will be easier. So suppose you are given this type determinant 2, 3, 4, 5. So what do we do? In that case, we cross multiply 2 into 5, we put minus sign, then 3 into 4. So this will be equal to 10 minus 12, that is minus 2. So for 2 cross 2, it is very easy. Now let's see 3 cross 3. 3 cross 3 means here, suppose 1, 2, 3, 4, 1, 5, 2, 3, 6 we are going to take. In that case, what you do, here you have to consider this is positive, this is negative, this is positive. Why? The reason I have explained you in the beginning also, you can check the position. This is A11. We write A11. If sum of the subscripts is even, then positive sign. Here it is A12. A12 means first row, second column. So sum is odd, so negative sign will appear. And here A13, sum is even, so again positive sign will appear. So this thing you have to keep in mind. I will tell you in detail later on. So we take this 1 and then we leave this column and that row. So whatever is left, we write it with a determinant. Then we take second one, again we leave that column and that row. So 4, 5, 2, 6 is left. Then we write last one 3, and then again we leave this column and that row. So 4, 1, 2, 3 is left. Now as you know how to evaluate, 1 into 6 minus 3 into 5. So 1 into 6 minus 3 into 5, and then minus 2 here, this is 6. So 4 into 6 minus 2 into 5, and plus 3, 4 into 3 minus 2 into 1. Just evaluate, you will get. Now suppose the same we consider in form of vectors. Suppose we have to find out cross product of two vectors. Suppose vector A is given as I plus j plus 2k, and vector b is given as I minus j plus 3k, and we need A cross B. Then what do we do? So for that, we write here I, j, k. Then write coefficient 1, 1, 2. Then 1, minus 1 and 3. Now, again same thing, write here I cap and then determinant, then minus j cap, then determinant plus k cap, and then determinant. Let's put the values. So this column, this row should be left. So 1, 2, and then minus 1 and 3, then this. So 1, 2, 1, 3, and then for k, sorry, I'm mistaken. Here I have written. So minus j, and we are leaving this 1, 2, 1, 3, and then this one. So 1, 1, 1 minus 1, 1, 1, 1 minus 1. I think you have understood. Now let's evaluate it. So I times 3 plus 2, 5, minus j times 3 minus 2, so 1, plus k times here minus 1, minus 2. So it is a vector 5I cap minus j cap minus 2k cap. So suppose this is vector C. So A cross B is giving another vector, and this vector will be perpendicular to these two vectors. I think you have understood how to evaluate cross product of two vectors. As far as dot product is concerned, you know very well. Suppose you are given like 5I cap minus 2j cap plus 3k cap and dot, suppose 9I cap minus j cap plus k cap. Suppose you have to evaluate. So here in this case it is very simple. Only you have to multiply the coefficients of I, j. So 5 into 9 minus 2 into minus 1 plus 3 into 1. So dot product is simple. Cross product is a little complicated, but you can do that also. So up to here it is very clear. Now linear velocity and angular velocity, this concept we have already studied. That suppose if we consider circular motion, in that case suppose this angle is theta, this is r, so, and this is this is radius, this is arc, then L upon r equal to theta, from where this is previous concept, L equal to r theta, or we differentiate it, so dl upon dt equal to r d theta upon dt, and from there dl upon dt is linear velocity, so we write v and r, and this is angular velocity omega. So this was the basic relation that we have studied earlier. And now dv upon dt, further we differentiate it, dv upon dt will give r d omega upon dt. So this will give dv upon dt equal to r d omega upon dt. This is linear acceleration A equal to r times this is angular acceleration. So these were the basic relations that we have already studied. Now there are some more concepts related to circular motion that we are going to study here, but for today's lecture we will limit our studies till here. So v equal to omega cross r, as far as here whatever we have written, I think you remember, as I told you, that v equal to r omega in magnitude. But if you write in terms of vector, then keep in mind v is omega cross r, right? And we have seen A equal to R alpha, but vector A will be equal to alpha cross R. So we will study some numericals based on these concepts in next lecture. Here we can read this line. We note that for rotation about a fixed axis, the direction of the vector omega does not change with the time. Its magnitude may, however, change from instant to instant. For the more general rotation, both the magnitude and the direction of omega may change from instant to instant. Angular acceleration, as I told you, alpha. So now another concept like moment of force, that is called torque and couple, etc., we will study in next lecture. I think you must have enjoyed. Thank you. Team Educate.